Anyways, I'll wait another about 10 seconds for that, and I'll go ahead and start giving the intro. So basically, yeah, right there. Thanks, Alan. So basically, we decided that, hey, a year ago, and some change, we were trying to reproduce the Rømer method because we do a lot of like research into the historical development of physics and astronomy and how we got to where we are today. Old Rømer is credited in like the 1680s, I believe, with being the first man to measure the speed of light fairly closely, and he used the eclipses of Jupiter's moon Io. So what he did is he plotted several of Jupiter's Io eclipses throughout the year and compared pairs of those to try and deduce the maxima and minima in terms of the timing windows. And he took the difference between the maxima and minima and came up with a delta value. And he correlated that to the speed of light. So the time that Rømer got was about 22 minutes, which, based on the astronomical unit and the distance to Jupiter that's accepted, gives a speed of light of around 220,000 kilometers a second. So he got 220. The real value is 300. Okay. Now, the reason that it said historically that he did not get the correct value is because it was the 1600s and he didn't have a good enough data set, a large enough data set to be able to crunch enough values to normalize the data to the correct value. But now that we do, we're like, man, I don't think anybody else has actually done Rømer's method with modern data. This was a year ago, mind you. We looked and we found one guy on YouTube who tried to do it and couldn't get it to work. I decided to do it manually using Stellarium. And when I tried to use Stellarium and literally measuring it with my eyeballs at the exact pixel frame that the eclipse would happen, which is the best way I could use a Rømer method, right? Also couldn't get it to work. I also got like 20 something minutes, and I was like, I don't know what's going on here. So we decided to use the JPL ephemeris tables in order to just do everything mathematically. We don't even have to use a visual, right? We can just use raw math numbers and plug it into a calculator and do it that way. And it'll be way more precise, and we can have the complete data set, 600 and something eclipse values over like
Can
a
I just have
3 year
a quick
period.
hands up? Can I just have a quick hands up of anybody who's got a fucking clue what you're talking about right now? Because
Yeah,
my hand is so not up. I've got not a fucking clue what
okay,
He's
well,
anybody
talking about the
is.
eclipse cycle for Jupiter's moons and using it
IO,
to
yeah.
derive the
Eclipse
speed of
cycle
light.
from Jupiter's moons. Okay, hang on.
Hmm.
Yeah,
So
Yeah.
back me up. Yeah,
Yeah, you
make
got a
more sense with that.
synodic,
So
you got a
so
synodic mapping
Jupiter's
between the
moons,
moon and Earth as well. So you can look that up.
Jupiter's moons cast shadows across Jupiter's surface, right? So we're
no, no,
saying
no,
Jupiter
no, no,
getting
no, no,
eclipsed?
no, no.
No,
It's
no, no.
the moon passes behind Jupiter and goes into Jupiter's shadow, and the moon gets eclipsed. And you can see this with the telescope. It's what Rømer was measuring. This is what's known as Rømer's method. So, anyways, when we did this using the JPL ephemeris data, right? It's a much more precise method. We can measure every single eclipse that occurs in an entire year, and then we can do that same thing for 3 years straight, and then plot it out. And what we found is if you'll go to page, scroll down a little bit, Alan. Keep going. There's like another graph. Just go to the next plot, next plot, next plot. I think it's page 8. Oh, yeah, there you go. What we found is when we plotted it out, we did not get 300,000 kilometers a second, like not even close. And not only did we not get 300,000 kilometers a second, we got about 460,000. But the 460,000 that we got had a major sinusoidal variation in it. And I'll get to that in just a second. So, based on the delta
What's
value,
what's got a sinusoidal what, hang on. So hang on. So are we accepting for this that Jupiter's a physical body? Is that where we're going? So if Jupiter's a physical body, it's got physical moons orbiting behind it. When they cross into darkness on the far side, the timing of that you're calling ephemeris data, and that's got a sinusoidal pattern. Am I following? Have I got that correct or anything close?
the timing of that comes from the ephemeris data, and we can take that timing data and plot it out across a year, and take the minima and maxima time windows of the pairs across the year when Earth is closest and furthest from Jupiter at each 2 points around the circle. And when we do that, we get a delta between the closest and furthest times, and that delta, when we average that delta out across a year between all the pairs, should should come out to be 17 minutes and like 42 seconds or whatever it is. But
According to who?
according to NASA, that's
Look
what
at
the
the
light timing
heliocentric
corrections.
model.
Yeah, the heliocentric model, bro. This is what the Romer's method is.
Oh yeah, show me that then. Show
This
me
is
the person
okay.
saying it
I
should
don't.
be a
Hey,
different number.
Hold on a second. I came to
That's
present
the only
this, not for
question.
you to interrupt everything. So I'm going to continue laying
That's
this
the
out.
that's the meat. That's the
Yeah.
bones. That's the whole
Yeah.
thing.
So
All
hey,
right, Kels, let's just let him finish the presentation. It sounds
But
like he
NASA
wants
says
to
something that's
go
wrong.
through
Where
it.
does NASA say the wrong thing?
All right,
Surely that bit's here.
let's just let. I mean,
Okay,
Giza, if you
sorry,
want to
sorry.
finish it without like
Yeah,
a whole question and answer thing, let's just.
yeah, I want to continue.
Sorry.
So, anyways, if please go look all this stuff up on your own time. You know, after I finish, I encourage you guys to. This is what Romer's method is. You can go look up Romer's method. You can watch it. There's hundreds of videos about it on YouTube. You can go watch it. Okay, it is established as an accepted fact in astronomy and a necessarily valid method, mind you, in astronomy. So, anyways, when we did this, we ended up getting this red curve. Okay, so what this red curve represents is the signal in the delta of that time window from Io's moon. Now, what should be happening is that blue graph. Okay, that blue graph, right? That blue graph would be what you would get if it was actually C. If C was actually C. Okay. Now, what we got was the red one. Okay.
Who's we? Sorry,
Me,
I'm not meant to ask things. Sorry.
the presenters. So, anyways, when you take this red graph, okay, and you take out just use because the red graph is actually the full signal of all the 600 and something pairs that we or 600 something eclipses that we mapped. When you take just the delta value and you correlate that to a time and a speed of light, it comes out to 460,000 kilometers per second, which is the yellow graph. Okay. Now notice that the yellow graph and the red graph are not perfectly overlaid. What this means is simply adjusting the speed of light to a different value does not perfectly produce the red graph. There's more than just a speed of light anomaly in it. So if we were to adjust the speed of light to be 460,000 kilometers a second, we still wouldn't get the red graph exactly. There would be a residual. Alan, could you please go to page 2, way back at the top, that very first graph? So by subtracting the red graph and the yellow graph, okay, we end up with this, okay? Now, what we end up here is we've got this residual, okay? Now, this residual is about 436 days of a sinusoidal period. It has a periodicity that's sinusoidal, whose maximum amplitude is about 436 days. Now, it says in this graph, if you look at the top left, about 399 days. I'll tell you why here in just a second. So, that blue graph represents, that blue line represents the distance between Earth and Jupiter. So when you plot the distance between Earth and Jupiter, the synodic year, the Earth-Jupiter synodic year, against this red graph, look how closely they match. Okay, when Earth is closer, you get a greater magnitude on the red graph, and when Earth is further, you get a lower magnitude on the red graph. Now, if you scroll down a couple pages, Alan, there's a bar graph. The bar graph right here. Okay. That data peak, where it says data peak, that black dotted line, that represents that red waveform we just showed you. Now here's the interesting thing. We were like, what possibly could be coming up with a 436-day graph? Because when we compare it to the Jupiter synodic year, it's really close, but it's not exact. So what we did is we decomposed the signal in order to compare it. So we said if we were to take the 365-day Earth solar year, and we were to take the 399-day Earth Jupiter year, and we were to take those two sine waves and add them together and superimpose them, would it match this? And when we did that, if you'll scroll down, Alan, we found that it did match between 91 and 94% for both Io and Europa. So, yeah, keep going down. Yeah, keep going. So, Io and Europa both have, keep going, both have a sinusoidally varying perturbation in their orbits, leading to these eclipse timing differentials that is correlated over 90% to Earth's position in space. What does this mean? Well, it means, first of all, that the heliocentric model cannot possibly account for this because the eclipse timings of Jupiter's moons are calculated from the JPL ephemeris purely from the Sun, Jupiter, Io geometry. Earth's position does not matter whatsoever, and you can even do the gravitational calculation for Earth, which we did. Earth is far too small and far too far away from Jupiter to matter at all. It only has the power to move Jupiter's moon by about a millimeter, which is not changing anything. So you cannot possibly account for this whatsoever in a gravitational model. So the open question that this data produces and creates for us is, why on earth is there an Earth-anchored correlation in the eclipse residual sinusoidally varying periodicity that maps to Earth's position in space? There should not be a correlation at all. It should have nothing to do with Earth. There should be absolutely zero overlap. But yet we see that that residual signal in Io's perturbation is 91 to 94% made up of Earth's position in space relative to Jupiter, or Jupiter's position in space relative to the Earth.
That's
If you
it.
were, if
R.I.P.
this was
Globe.
true, if this was true that it happens from Earth to Jupiter, right? Like now, this is interesting, right? Because what this implies is it implies that there's some Earth anchored preference here in this modeling. In a heliocentric model, if somehow Earth was affecting Jupiter's moon Io, then Jupiter should be affecting Earth's moon, but it doesn't do that. And you can do the gravitational calculations for both, and in both cases, the Earth would only affect Io by a nanosecond, an order of a few nanoseconds, and Jupiter would only affect Earth's moon by milliseconds. So in neither case can any gravitational interaction between these bodies explain the perturbation of Io or Europa. Both
Are we
Io
accepting for
and
this? I'm sorry, it's
Europa,
really going on.
both Io and Europa experience this. So if
Europa.
you'll scroll down, Adam or Alan,
Europa, like Europe.
a little further. So right here, scroll back up. So right here, we decided, okay, we're going to check some of the other ones, some of the other
We?
moons, if we can check all the other moons throughout the solar system, if there's any correlation. What's odd, what we found that's odd, is there is a little bit of a correlation with Ganymede, but for pretty much all the other objects in the solar system, this did not occur. So something is interesting that's happening with both Io and Europa. If you'll scroll down, we'll go to the chart past this one. No, it's the next one, I think. After this, it's the tape. Sorry, the tables. Yep, right here, right here. So this right here, this is interesting. If you look at the gold and green plots on the left-hand side, that gold plot, okay, that gold plot is the residual, the perturbation residual signal in the moon. That green line plot is the sinusoidal period of the Earth-Sun year combined with the Earth-Jupiter year. And if you'll notice, on the x-axis, the time axis, the peaks of these two curves align almost perfectly. There's a 91% for Io and a 94% correlation for Europa. When you subtract the difference between these, what's left over is the purple plot, which we don't know what the, as of yet, we don't know what's contributing to the purple plot. We don't pretend to know a cause. But what we do know, and what we're presenting preliminarily to all you guys right now, while we continue to work on it to formalize this, is that there's absolutely no possible way in the heliocentric model that the eclipse timings of the moons of Jupiter should have a periodicity component in them that is 91 or 94% correlated to Jupiter's position with respect to Earth. at all. And yet that's a fact from what we see with the data. So that's what we wanted to present to you guys. We can't make any claims about the cause. All we know is that it absolutely shows that either the distances or the dynamics themselves must be wrong. Otherwise, this would not exist within the heliocentric model.
Hey, Globe.
But if anybody has a few questions, you can ask a few questions, and I'll take a few questions. But
Who's the we? You keep saying we, the presenters got this data.
I have a question.
Yeah. Yeah. It's a wild evidence.
yeah, so
It's a
this would be
very
called
strange one.
maybe you don't understand. This would be called an internal critique of the heliocentric model, because if the heliocentric model is true, then necessarily everything that follows from it must be true.
Was that the conclusion of the people who did the actual research?
The conclusion of the people who what are you even talking about, eggshells? I don't think that
I have
you
a better question.
You got
Yeah, I
some
don't-
research from some people. Was that their conclusion? It's a
do
pretty
you
fucking
do you
straightforward
realize that
question.
maybe you don't understand that you're able to critique a model without believing in it?
That's not the question. The question, you're saying I'm doing an internal critique, which is I'm taking this internal model, I'm showing it's internally inconsistent. You're
Yes.
showing work from people who did that work. Was it their conclusion that the model is internally inconsistent? Or did they say this is consistent with our model? That's an important question. What do you mean you don't know the answer to that question? Did they say this changes our views on the speed of light, or the shape of the Earth, or the distance of the orbits? What did they conclude from this is a valid question.
Who do you think
What did they
you're talking
conclude?
about when you say they?
The people who actually did the work.
What work?
The people who actually came up with these graphs showing this ephemeris, the JPL, whoever they are.
Oh, you
What was
mean
their
the
conclusion?
JPL ephemeris data. Oh,
What was their
okay.
conclusion? The
So-
paper that you're quoting from, the one you've got on the screen, those people who wrote that, what is their conclusion?
Oh, the conclusion is what I just gave you.
That the Earth, yeah, fill me in.
Yeah, that the heliocentric model must be wrong in some way, either in terms of the distance or the dynamics.
Who's JPL? Somebody's
Jet-
doing a neo-Tychonian
Jet
model. Who's JPL?
Propulsion Laboratory.
Yeah, so I mean, like, you're just embarrassing yourself at this point
Sure.
with these questions. JPL
Sure.
ephemeris is the most renowned ephemeris data that's in existence that's used by NASA right now.
Sure. And what's their conclusion?
They don't have a conclusion about this, eggshells, because what this is this is taking a data set and using, and up until now, a method that hasn't been used since Rømer's day with the modern updated data to internally test the model. So JPL ephemeris data, everybody has access to it. It's public. To our knowledge, no one has used the JPL ephemeris data in order to perform the Rømer method. So that's what we did. Because if
And
the
you
Rømer method was valid in the
performed-
if the Rømer method was valid in the 1680s, it would necessarily be valid now. No one can
Why?
test its
Hang on.
validity.
What? Hang on. If something was good in the 1680s, it's still good now. Show me that with one other thing from the 1680s. Maybe an axe. Maybe you could say there's an axe hasn't changed much, but
Stellar
fucking
parallax,
everything has
stellar
changed
aberration,
since
the
the
illusion of
1680s.
Venus.
He did
Wait,
not
wait,
say
astronomical-
1680. He said
Yeah,
1960s.
you know that
Sure,
they use
everything's changed since the 1960s
this.
too.
You
Methods
know that
get
they.
better.
Well,
Hey,
you were
can you
200
stop
years
close?
off, my
Yeah,
friend.
maybe
It doesn't
you
matter.
should go
Things get
research
better.
more.
He's
Eggshells.
saying his
So
Like
lads,
300 years.
lads,
Can I ask my simple question?
One second. We're all talking over each other here. Give us a second. Piezo, you were about to say something?
Yeah, they used the occlusion of the moon, or the eclipse rather of the moon of Jupiter, to produce the system known as longitude. So if you want to claim that Rømer's method is invalid, you have to literally throw out latitude and longitude. Thank you very much. Your silence is deafening. I love it.
Yeah, no,
I'm
sure.
not-
You used a method they didn't use and that hasn't been used for a while. That's fine. Yeah. I just don't.
It's all good.
I've got
I
no
don't quite see
math.
it. So you've got modern data from the JPL ephemeris data about the eclipses on Jupiter, and you're applying Rømer's method. is Rømer's method still used? Why aren't they doing this? Why is this work being done from the outside? Why is nobody thinking to use Rømer's
Eggshells, let
method?
me
Is
ask my question
is
first.
it
You're
they
asking
haven't
6
thought of it?
questions.
Is it they
No,
haven't
it's
thought
because
of it, or is it
Rømer's
that a
method
better
was
method
used
now
to
exists?
Rømer's method was used to determine A, the speed of light, and B, longitude. And so we already know those things independently, separately from Rømer's method. So there's no point in using Rømer's method to do those things when we have modern data. But what we did is we said, okay, well, if we were to go back and use Rømer's method again with modern data, would it still give the correct answer? And it does
does it?
not.
Okay.
No, that's the whole
But
presentation.
what have you found? You found that using an old method gives the wrong information. What do you
No,
want from that?
well,
Maybe that's why they don't use this method anymore.
no, they were specifically using it to derive longitude. And if the speed of light, the way that they say, is correct with the distance offset that they have, because when they look at it from the Jovian centric view, they account for a 33 to 53 minute timing difference for the speed of light to travel from the sun to Jupiter at the accepted astronomical unit distances. So we should absolutely be able to derive the speed of light from the timing differences of the eclipses
Why are
from
you
a
doing from the sun?
one second, please don't interrupt in the middle of that. That's to describe how long it takes for the light difference in their model to travel from the sun to
From Jupiter to the
Jupiter,
Earth.
yeah, and then back to us. So that's I just muted you for a second because you're just talking over me in the middle of me trying to explain it, and that's not going to be useful for anyone. So if I have to mute you, like I will, but if you could just let me finish explaining this, that would be super dope too. Like either way is fine for me. So just let me know. So anyway, that's the accepted timing difference that they have for distance wise for the speed of light over the astronomical unit to be at Jupiter's accepted distance. So we should be able to derive the speed of light from the eclipse's timing difference as well, the same way that Rømer was trying to do it. And because we're using the JPL ephemerises, we have the most accurate and updated heliocentric versions of ephemerises that would be possible. So when we take the whole data set, we should definitely be able to derive C using those distances, because, and the fact that we can't derive it from that, and if we try to derive C not assuming any distances and just doing it naturally from the eclipse timing, we get a value that would have to correspond to 400,000 or 475,000 kilometers a second to get it to fit in. So there's a huge contradiction in just that alone. And then the sinusoidal perturbation thing is a whole separate argument in and of itself. But just the method of it working the way that it worked and the way that it was used to determine longitude for celestial navigation back then, it's still valid. It's not invalid. And it's the way that you, algebraically solve for it, or what the speed would be for the propagation rate based on those distances. It should come back to be C. Anything other than that would be a direct contradiction of the model.
Yeah, velocity equals distance over time. So if the velocity of light is known and the distance to Jupiter is known, then you should be able to plot a known timing difference. And when we actually take the data and we plot the timing differences using the eclipses and we compare it to the known distance, we don't get the right speed of light.
Distance over time is speed. Velocity is a vector.
Okay, that's nice. Thanks.
If I may, you mentioned the Earth's not relevant to it. However, the actual method that I've just posted in the chat says it's made by observing Jupiter's timing of the moon, noticing delays when the Earth moved away from Jupiter. So you appear to have dropped out of your calculations the actual one of the operating principles of Rømer's method, and it says albeit lower accuracy too. So I feel it's a bit snake oily. I'm sorry.
I still don't understand even what's
Nothing you
wrong.
said
Are you
has
saying
any
the
meaning
speed
or
of
value,
light?
bro. You don't even know what our data is. You haven't even reviewed it. We just gave you a presentation. It's the first time you've seen it, and you just made up something on the spot that you don't even know what you're talking about.
I want to try and understand it.
Doesn't move. You said the Earth doesn't move, dude. So
Yeah. Let's. All right, players. I hate the game not to play it. So let's go back to talking about the game. I'm a data scientist. We talked about data set. We talked about conclusions based on parsing that data set. So I want to talk to that point. Someone brought up a very good point, which is to say, like, we got all this new JPL ephemeris data. Why haven't, quote unquote, they done anything about it? And I would put it to you that we have just so much more data this time. The sensors are better. We had better compute when we sent out our things that have said sensors on board. It's a phenomenally large data set. Now, the data set they were working with in the 60s was contingent on, well, the sensor arrays and the ability to power them and parse them into, siftable data. It was minimal back when they came up with these calculations. So, it was also slower back then because they were chunking through, what was then a giant data set. But now we are literally dealing with something that is orders of magnitude greater. And
It's not the
like,
1960s. The Rømer method is from 1676.
It doesn't
is
matter
it
when the
okay?
method
Okay,
is from,
I
bro. It's
was wrong.
literally just a
It
distance
does.
over time calculation.
Sure, no, I agree. But what I'm saying is
Thank you,
distance over
Gregory.
time. Yes, yes, I agree with the forms. The distance over time thing, yeah, great, but we just have so much more fucking data. Is it really from the 1600s? I'm like literally, I don't know.
No, the data is not from the 1600s, bro. Like y'all,
But
do
the
y'all
format,
listen? Like seriously,
I,
put your listening ears on
do
like
you
we're in
listen that
kindergarten.
I am asking a
The
question? I am
the
admitting
JPL
I lack
data,
data.
the JPL data is current as of 2026. It's
Sure,
updated
I
live
understand the
24/7,
data. I'm talking
365.
about the Rømer method.
Yeah,
I
the
was
Rømer's
less than
method. Yeah, he was
16.
the first. Yeah, he first did this in like the 1680s, I want to say.
Okay, I'm sorry earlier, Broken Eggs guy or whatever, for scoffing at what I thought was a misquote. I thought this was more like freaking space program error, but 1600. Cool. I need
I
to
never
read
want to hear the name Eratosthenes again from eggshells.
up. Gotcha. I'm gonna read up, but the point is like, there's a giant data set, and then like once it's been parsed, well, it'll be parsed again by another group later. There's not going to
Yo,
be some like base truth that comes out of it. This won't update the gospel or whatever. This will just be, one more brick in the wall of
So you think that
understanding of reality.
the speed of light being like off by like 56% is like not a big deal?
I didn't make any claims as to speed of light. I was merely talking about the data science angle.
Or like
But
the
that's
distance to
interesting.
Jupiter
I
being
don't
off by
know.
56% not being a big deal?
I mean, it's interesting when we get new calculations. We did the like well of Sen and thing when we calculated the circumference of the Earth, and then got a little bit better once we had like satellites and stuff. But
Yeah, so like, you weren't addressing the point, you were just saying the words, so that's
well,
zero, thanks.
you addressed a point that was never raised. So Darvo.
no, that's not the same thing. We're presenting some data. If you have questions about it, how we got to it, and etc., trying to come
No,
up,
I love
I've
trying
got
to
some
come,
questions.
1 second, trying to come up with an on-the-fly explanation to it by repeating the word data set over and over again is insufficient and superfluous. So we can go ahead and skip that. And if you have an actual question about like what
Sure.
Rømer did, how it was used, all of that would be super useful so that you could understand what's being put forward. 1 second, Egg, I'm almost
Does
done.
JPL? So here's the question: does JPL use it for observers on Earth, or is it from time of emitting from the?
You can take the JPL data set and calculate it from any frame in the solar system you want to.
So you've taken JPL stuff and then time corrected for where Jupiter is in its orbit.
Well, actually, we did it from both.
They actually time corrected already so that it comes out to be 33 to 53 minutes for where Jupiter's at on location wise. So that's why it should also come out for the speed of light to be derived in that way based off of the actual eclipse data. They should match, they coincide together, and they do not.
Right, they already.
So what I'm reading here, I don't know
Eggshells.
anything about this.
Hold on.
I
Yeah,
just
okay.
want to respond.
So maybe I don't know anything about this. I just want to respond and try to refute you with no knowledge. Cool. I'm trying to clarify it. So as Alan just said, it's the timing correction is already built in. When you take the Earth-centric view, right? And actually, we did this in both the Earth-centric and Jover-centric views, just so you know. But if you take this in the Earth-centric view, there is already, when you look at Jupiter, there's already a timing correction built in for the distance between Earth and Jupiter at every point in time throughout the year. And when you do this, that means that we don't have to account for any other timing changes to the light signal. The light signal is already C equals C. So therefore, when we look at the moon go behind Jupiter, now we can just take the raw timing that happens and take the delta function of the pairs across the year and come out with the signal. And it should be
This
a
is just
delta
garbled
of 17
nonsense.
minutes, but
This
it's
is just
not.
garbled nonsense. Let me ask the question, because that's
No,
just
it's
garbled
not.
nonsense.
You
We
just
don't know
making
what
this claim is stupid.
But we don't know what any of those letters mean. You haven't explained any of it. It doesn't make sense to anybody. Even if a mathematician was sitting here, they wouldn't have understood it because you didn't label any
I
of the
mean,
fucking things. You
once
just made it
again,
sound
once again,
mathematical.
stop. Okay,
Let me
this
ask
is
you.
lit-
Let me ask you
no,
a direct
no, dude,
question.
shut up. I'm not gonna sit here and have you just
You don't
make
want
up
to
a bunch
answer a
of. First of
direct
all,
question.
no,
Okay.
all you're doing is insulting,
No
bro.
questions.
If all you're doing is insulting,
So,
like you're not
one second.
engaging in good faith. Anybody who is in good faith, this is what they would say. We're going to go back and review this data you've presented. Can you share it with us? This seems alarming or at least interesting. Maybe we're going to go look at it and get back to you. You're not doing that. You haven't even looked at it. You're saying, I don't know anything about it, but I just know that you're wrong. Dude, shut up.
All right, so can you entertain my question now? Sweet.
What's up?
I still didn't fully understand when you were explaining it. You're saying that
Okay.
the speed of light before it gets eclipsed by Jupiter. So you're measuring the speed of light before it gets eclipsed and after?
Not exactly. So what's happening is if you use Rømer's method, right, what happens is Jupiter is some far distance away, right? And at that distance away, it takes a certain amount of time for the light from Jupiter to reach your eyes. Okay. So what Rømer did is he said, okay, so if I take an eclipse of Jupiter's moon, right? And because we know that we know what the period is, we know the period of Jupiter's moon. It's like 1.77 days or whatever. So if we take the timing of an eclipse from Jupiter's moon when Earth is really close to Jupiter, and then we take another eclipse timing when Earth is really far away from Jupiter, those should be offset in time, the time that we see the eclipse occur from our position on Earth. The difference in time between those should be the distance to Jupiter divided by the speed of light. So
You're
when we
talking
did
about if I was an observer on Jupiter,
no on Earth.
the moon is eclipsing the sun? I'm sorry, I'm still
No,
not getting it.
no,
Okay.
no. I'm on Earth. The sunlight is shining on Jupiter. Jupiter casts a shadow behind it. The moon of Jupiter moves into the shadow and gets eclipsed.
Okay, thank you. Yeah.
Like years later, numerous scientific groups followed the findings of its experiment, refined it a little bit, and basically confirmed that the Rømer method was valid. Very interesting. There wasn't a whole lot of people like thumping their chests and trying to convince other people. Trust me, bro. We had that one good time that one time, so believe everything I say.
I had a question about the eclipses there.
Yeah,
What's up, Bull Knight?
So the eclipse is only defined as when a moon enters the shadow of Jupiter. It's not when it's just occulted by Jupiter, right?
We did it both the entrance, the exit, and the midpoint, just to see if any of those would change the values, and none of them did.
And there would be cases or configurations where two of those would, well, you'd never see it when it's at the midpoint from Earth. I don't think. Yeah, maybe you could if it's on like the extremes, but there would be cases where you wouldn't be able to see. It would enter the shadow behind Jupiter from Earth's point of view, so you wouldn't be able to see that, right? But because you're using data, you can know when it happens.
Yeah, so yeah, when we use the JPL ephemeris data, like we can actually see the first moment the disk of Io begins to eclipse versus the first moment it begins to emerge, the last moment it begins to eclipse, the last moment it begins to emerge, and then like when it's half eclipsed or half emerged. We checked all three of those different options, and it doesn't make a difference.
Yes, but what I'm saying is there would be configurations between the Earth position and Jupiter's position where entering a shadow wouldn't be visible because Jupiter itself is in the way.
Right, which is right visibility wise, right, which is why and that's one of the difficulties. I'm glad you brought that up. That's one of the difficulties with Rømer doing it, because technically, right, the angle of Earth between Jupiter and the sun, right, can like affect the visibility of the moment of time, which led to inaccuracy. Which that's the accepted reason. That's one of the accepted reasons as to why his method wasn't able to be perfectly accurate. Because if you just view it from Earth, you don't totally know. Which is why it's much more useful to use the JPL data set, because you can actually do it from the Jovicentric position and just literally only use the geometry of Sun, Jupiter, Moon, and that's what
Yeah.
we did.
Closer vantage point. Yeah, I think I always do the also awesome analysis. I always like to do the kind of like, okay, how fast forward 10 years, how do we extrapolate? How do we scale up the thing? I mean, it's amazing this guy was able to do this in the 1700s or the 17th century. And then it's awesome that we've gotten something close there because engineering has gotten to the point where we can do that. So then I think maybe the extrapolation from this, JPL ephemeris data 2.0 or something like that, would be get a system of satellites out there so that you could measure pretty close to the exact positions of the moons and then match them up with the perspective from Earth or
Bro, that's
James
what
Webb.
the JPL ephemeris is. JPL's
How,
ephemeris
how,
is literally
okay,
every
okay, okay.
observatory on Earth, every satellite in the sky, every probe in space, all of their data fed into one stream, into one source is the JPL ephemeris.
Yeah, but I'm saying 10 satellites around Jupiter, for example.
I mean, your argument.
Yo, my dude
Is
said, but
that
more
enough?
satellites. Nah, dude, that's not.
Yeah, exactly. That's how
Nah.
photogrammetry works.
You
More
think that the
vantage
JPL
point.
Okay.
ephemeris data is so wrong that it's going to make the speed of light off by 56%, bro? Like,
No, I didn't. I never said anything like that. I was just making a case for what more data might give us. I think it's amazing he figured this out in the 17th century, and it makes sense though because Jupiter has so many moons. You don't have to wait for some specific celestial event. You just have to have an idea of which one is which
well,
peaking
yeah,
out.
I think
yeah, they picked it. They picked it because Jupiter's moons are like some of the brightest objects in the sky with
Yeah,
with a telescope, and they eclipse very often. They eclipse every 1.7
yeah,
days.
yeah,
So
yeah.
that's
And
the
then there's
reason it
no
was chosen.
yeah, there's no accretion disk like with Saturn, even though Saturn has way more moons. It's more crisp. Makes sense.
Has
Yeah, yeah.
the
It's
Alan
so funny.
okay,
Oh,
sorry.
sorry, Bull Knight. Sorry, go ahead, man. Go ahead.
Has Alan or Goose double checked the ephemeris timings in your data with their C stars, just like it'd be interesting to cross see it happen as expected per the graphs.
Dude, if you want, we have an addendum report that actually shows the full methodology used and all the different checks that went through this to make sure that there wasn't some systematic error in the data.
Yeah.
We can give you that if you want to look over it.
Yeah, whatever links you got would be sweet.
Sure thing, brother.
I know I can see at least 3 of Jupiter's moons with a $4 telescope I got at Goodwill, even inside a city. So
Right.
trying to there should be some configuration where that would be visible from pretty much anywhere, or
Yeah.
with almost no money outlay on equipment.
Well, and once again, right? Once again, one of the reasons that we decided to do this with JPL, because that was the solution to the problem, is just what you said. Your previous question, based on where the geometry of Earth, Jupiter, Sun is. Sometimes the way that the shadow is angled will cause an eclipse to occur at a time where it's not it's not normalized from the Earth vantage point. And so that's why we're well, wait, if we just use JPL, we can look at it from the Jovicentric view. Normalize anything, everything is just raw angles with the sun in a straight line between the sun and Jupiter. So that's the most accurate way to do this, and that's what we did for this data set. And when you compare the data set from the Jovicentric position to the Earth-centric position in JPL, because everything is derived from the closest thing you could get to a God's eye view, basically in the sky in the solar system barycentric model, it still comes out to be the same answer because they do light timing corrections. And even if you can't visibly see it from Earth, all of that is still baked in naturally to the mathematics that they have, so that when you average it out over a full year and a full 3 years, which we did in order to do the solar year and the synodic year cycles, when you average it out that way, it still comes out to the same answer.
Yeah. Cool. And one small quick question: what are the thick parts on the top and bottoms of the red plot? Those thicker air regions. Does that relate to anything known?
Which Alan, can you
Like
scroll
the
to?
top left that's on there that Alan has up right now.
Oh, Alan has up right now. Oh no, go
What
back
am
to
I
it.
doing?
The gold plot.
Oh yeah, that's gold in this one, isn't it?
Okay, the top left gold plot. So, let me see. Detrended eye. Okay, the little like the little thick thing.
Yeah.
Okay, I think if I'm not mistaken, I think that's when you plot it. There's like a like the thing that you're talking about, the the emergence and entrance are offset because the shadow is not uh like directly lined up from a way that we see it happen at the exact same moment. Like it doesn't always happen at the exact edge of the disc, right?
Yeah.
Sometimes it'll start from like the midpoint of the disc or something like that. I think that's
Mhm.
what that blur's from.
All right.
Um,
Cool.
yeah. I always like Bull Knight's questions, dude. Bull Knight usually gives good questions, bro. I do appreciate that.
When it's quiet enough to get a question in.
I know it can be. If there's no further questions, let's do one more round. If there's no further questions, we'll drop out here in just a second because we just wanted to come by and give this preliminary share to you guys, and it'll probably be a Prezi fairly soon, but just kind of wanted to give this preliminary share because this is actually like extremely like crazy. Um,
Could you
and
drop a link to the data set? This is really cool. I want to
um,
play with it.
Yep, sure will. Just got to finalize a couple of things.
Okay. Yeah, when you do, I'm looking forward to it. Do my Python thing.
yeah, bro, for sure. And we can also give probably at some point we'll also give an addendum form showing the the formulae.
Very cool.
But oh, so apparently Eggshells has been saying some stuff here in chat. I do want to address this. I don't want his questions to go unanswered. It's just he got muted because he's like not able to control his mouth. He like incessantly interrupts, but totally totally okay to put questions in chat. So to answer you, Eggshells, I'm answering your question about the light time corrections, right? So just so you know, the light time data set, like the light time corrections in JPL, are already present when you look from the Earth frame. So in the Earth frame, you don't need to do a light time correction, right? Because it's already baked in. Now, if you go to the Jovicentric frame, because what the light time correction actually is it's literally based on the speed of light, taking the time delay for what we see to get from Jupiter to us. Because when Jupiter is really far away, it takes a certain amount of time for that light from that moon to get to us, which is between 33 and 51 minutes in the heliocentric model. So that's already done for us. You don't even have to do it. If you transform to the Jovicentric frame like we did in order to get the most precise timings for this eclipse graph, then in the Jovicentric frame, you don't need a light time correction to Earth because everything is computed locally. The light travel time from Jupiter to Jupiter's moon is like such a tiny amount that it doesn't affect anything. So yeah, it's on the order of like a millisecond or something like that. So or probably less. It's probably no, it's definitely nanoseconds. My bad. It's on the order of nanoseconds. So there's no correction needed from the Jovicentric frame. We're not double counting times or double counting distances or anything like that. But anyways, that's all.
How do
Any
you
other?
correct
So,
JPLs to the
got a
Jovian-centric
question.
thing? They already did that for us. That's otherwise there wouldn't be they wouldn't say that there's a 17-minute delay in the occlusion and emergence, which would derive C in the first place, which would be based on a 31 to 53-minute timing difference to have the correct distance for the astronomical unit for Jupiter's position. Sorry, go ahead.
Yeah, I
What was your
mean,
question?
yeah. The difference between
Alan,
Jupiter and Earth is just changing your vantage point and then not having the timing correction that's present when you're looking from Earth. Because when you're looking from Jupiter, you're at Jupiter. There's no time delay from Jupiter to Jupiter.
Alan,
Um,
what is the time difference between the current measurements and the early measurements?
Ooh,
Is
great,
that time
great.
difference not according to
Yeah.
the shift of the magnetic field and the lens itself?
I'll know about that, but with Rømer, with his partial data set, he was getting 22 to 24 minutes, and using the modern stuff, you get what was it, like 12 minutes?
It's like
And
11
then,
and change, I think. Yeah.
yeah, and then you're supposed to be getting 17 minutes to correctly derive C if the corrections that they made to have C be compatible with the time of flight to Jupiter and then reflect back to our eye. If those distances are true, then the correction that they make should give 17 minutes for the differences. So yeah,
Yeah.
we're pulling like 11 to 12 minutes right now using the modern data.
Last thing, Alan, there's one more thing I wanted to show before we go. Can you go up to like page 8? I think it is. Yep. Okay. So page 8. If you guys will look at the graph on the left, on the vertical axis on the left-hand side where it says the 0 is, that's the seconds, the number of seconds that's added up over the year. That green dotted line, that's a horizontal line. That's the predicted that's the predicted signal that we should get, right? If C is C. So if C is C and we use the JPL dataset, which is extremely precise and continuously updated 24/7, 365, we don't expect to get any residual signal at all. There shouldn't be a residual, and if there is a residual, it should just be like a very tiny thing due to random noise. What we get is a periodic sinusoidally varying with respect to the Earth year overlaid with the synodic year signal in Jupiter's moons. So, like, just to recap, even if everything we did was completely wrong, which it is not, but even if we just had some glaring retard error, which we don't, you still would not have a signal that is a sinusoidally varying periodic signal, which is the superposition of the Earth solar year and the Earth Jupiter synodic year added together. And that is actually exactly what we have within 94%. So if there's no further questions, I will close there. Do you have anything else, Alan?
Nope, that's it. Thanks for elucidating this.
Yeah, this is great. I have one question just to bring it back to a point you brought up a few times. There was basically discovered a 56% discrepancy in C. Is that what I'm
It's like
hearing?
it's 53 to 58%. 53% is that gold curve, which is 460K.
Uh-huh.
58% is the purple curve, which is 475K kilometers per second. And the difference between those two curves is like we were figuring out, gold is just when you change the speed of light to try to match the delta T and the red signal.
Mhm.
And then we were like, well, that still doesn't match it. So what if we account for the eccentricity of Jupiter or, some little things like that? And when we did that, it barely changed it. It changed it to 475. So like neither one of those, totally accounts for it. Gold is just the raw change though, just accounting only for the speed of light variance. So that's the one that we're using as our number. But
Crazy. Yeah, when you get the data set, I'll try to replicate or find some variance.
yeah.
Good work. This is comprehensive. Nicely done.
Thanks, dude. Well, I'm gonna
Thank you for
leave it on.
sharing.
No worries, bro. I'm gonna leave it on that note. Here within the coming days, Alan will be publishing it once it's we get it fully polished up, and then you guys will be able to review it. This was the little preliminary beta pres. So
Looking pretty good for
right,
a beta. Science rules.
get the full. This is the pre-release or whatever. But yeah, we'll get it to you guys.
Pre-Prezi was right there.
What'd you say, Bull Knight?
Pre-Prezi was right there to use in a sentence. And
Yeah. All right, see you boys.
Later, lads.
Good
See you later tonight for the conceptual model review.